All right. Hello, everyone. Section 10.2, another chi-square test. This is a different type of chi-square test. This is called a chi-square test of homogeneity. The chi-square test of homogeneity, as you can see on my screen, tests whether it is reasonable to believe that when several different populations are broken down into the same categories, they have the same proportion of members in each category. So we have multiple populations, at least two, could be more. And then within those populations, we have some sort of categories. And what we want to do is see if those categories are broken down the same percent in each population. Okay, that's the test. It's going to look and feel a little bit like the goodness of fit test. It's got a couple of minor differences. The test statistics can be found the same way. That's why it's called chi-square test. It's still observed minus expected squared over expected. So as you can see, what I have here is I have this is an example from the book. This was three different brands. So you can see the word brand here. 3 different brands of paper towels, and they were being tested on spills. Okay, each paper towel had 25 tested. They don't have to be the same, by the way. In this case, they were. Mathematicians typically like them to be the same, but it doesn't have to be. And then what happens is we cleaned up the spill, and then we saw if the paper towel broke or not. So like for number 1 brand, 18 broke, 7 didn't, and then 7 of 2 broke, and then 5 of 3 broke. So this is a pretty obvious example. I think you can just look at the data and see, hey, it looks like there's a difference. But we're going to run a test to see if that difference is statistically significant. One thing we could do, I'm going to just show you here, is we could draw a little picture of this thing. This is called a stacked or segmented bar graph. Sorry, that should say or, stacked or segmented bar graph. Kind of gives us a little check. So you can see what I did was I broke up the categories, or the paper towels, 1, 2, and 3, and then the breaks in blue, the no breaks in orange, or whatever color that is. And you can see that there's a difference, right, by looking. So that this is a nice little visual. So that you might be able to draw a little. Might be asked to draw a little visual. One thing, if you notice on the side, I put the total number. That only works because of the fact that there were 25 each. You want these bars to be the same height. So typically, what you're going to put over here are percents instead of total counts. As long as your total counts are the same for each category, no problem. All right. But if they're not, if you got 50 of one and 100 of another and 60 of another, you're going to have 3 different bars heights, and it's going to be really hard to like compare, right? So you want those bar heights to be the same. So bar heights always the same, okay? And the way you can make that happen, even if it's not set up for you, is to use percents over there. 100% is the total, okay? So what does this mean? What's going on? Well, here's what happens. So first things first, we have this in a matrix. This is called a matrix. We're going to do this all kind of the slow way today. I'll show you a little quicker way in class. But the matrix, the numbers are in what are called a 2x3 table or 2x3 matrix. And the reason it's 2x3, let me show you, the totals don't count. Typically, we don't write the totals in there. They're just there for our purposes to help us what's going to come next a little bit. But the information would just be there. So the table is actually a 2 rows by 3 column matrix, or 6 cells. Okay, we want to know the number of cells in essence. Okay, how many cells? Kind of like categories in some ways, but not exactly. Okay, so the idea here is, what are we testing is, are the results consistent with the hypothesis that the breaks are the same for each brand, right? That's the chi-square test of homogeneity. 3 different brands. We have a yes or no question in essence that we're asking. We're not really asking, we're doing, but we might be asking in the next problem. And we want to know if they're saying yes or no, or they're breaking at the same rate for each brand. Okay? So all we got to do is this. It's going to look and feel a lot like the other tests. We just need to find the expected values in each one of those cells. Okay, assuming that our null hypothesis is true, right? Just like last test, the goodness of fit test, we had a hypothesis, which was some sort of model, right? So we have the same thing here. We have a hypothesis, which is some sort of model. And the model would say that, hey, these are all going to break at the same rate, right? So that would be my kind of like my model. So I got to figure out what that means. What does it mean to break the same? What are those numbers? Okay, this is kind of easy because they're all 25s, but I'll show you a general way so you don't have to So you can do it the general way. So again, this is what we observe, same data, okay? And so what we want to know is what we expect, all right? So what I did was I thought, well, look, they all need to be breaking at the same rate. That's the assumption. So we have to find an overall percent break. So if you look at my last column, 30 broke out of 75. Okay, 30 broke out of 75. So that's like the break rate. The break rate is 40%. So if the break rate is 40%, we expect each one of the categories, or the paper towels in this case, to break at that same rate. So I took 40% of the 25, and that would be my break, 10. Now, that's not number always going to be the same. In this case, they're the same, right? 10, 10, 10, because it's always 25 for the total, which means 15 not breaking. 60% is the not break, right? So this would be my expected values. Just remember that they're not always going to be the same total, right? So we just take that rate, and then we go from there, okay? The chi-square test statistic is found exactly the same way it was found in the last test. It's still, for each one of those 6 cells, we want to do observed minus expected squared over expected. So what we're going to do for now is we're just going to put the numbers, what I would do is put the numbers 18, 7, 5, 7, 18, 20 as list 1. Where am I? 10, 10, 10, 15, 15, 15 as list 2, and then do observe minus switch. So it's going to be a quicker way in class that I'll show you next time we meet. But for now, that's what you have to do. You have to just do it manually at this point. So I already did that on this one. You can check my work if you don't believe me. I got a chi-square test statistic of 16.34. So again, just like last test, we'd want to say, okay, is that 16.34 too big or not? Is it too big to reject the null hypothesis? All right, so it all comes down again to degrees of freedom in this particular problem. And the degrees of freedom is figured out a little bit differently in this one than it is in the other one, because they're not really categories. Okay, so I'm going to run you through, and I'll do degrees of freedom here in just a second, don't worry. I'm going to run you through a general test, and then we'll do a specific one also. Okay, so this is called a chi-square test of homogeneity. Okay, these conditions are independent simple random samples. So of 2 or more populations, in this case we had 3, so we need independent simple random samples. That's the first thing. Each outcome falls into one of several categories, just like the last one. Each expected value still has to be greater than 5 for each cell. We have to figure that out, just like the last one. Okay, those are the conditions. My null hypothesis, this is very general, right? It would be specific in our problem. The proportion that falls into each category is the same for every population, or for each of the populations. Again, we'll be very specific in our problem. So I would say for the tau problem, I would say something like the number of breaks is the same for brand 1, brand 2, brand 3. And we're going to do another example, which you'll see. My alternate hypothesis will be for at least one of the categories. They're not the same as the other ones. Okay. Find your chi-square test statistic the same way we've done it. Observed minus expected squared over expected. You're going to draw a picture, find a critical value, find a p-value, all the same way we've done before. So here's where we have a little change. Sorry, this should be degrees of freedom. Degrees of freedom is actually the number of rows minus 1 times the number of columns minus 1. Okay, so for our particular problem, it was a 2 by 3. We would subtract 1, so 2 by 3 means 1 times 2 would be 2 degrees of freedom. So it's not the same as the category. It's not like there's 6 categories, because there really aren't. So it's figured out a little bit differently on that one. And then we just go to the chart and do the same thing we did before. To find the expected values, I'll give you a little mathematical way to do this here. You saw what I did in the tau problem, right? Is I figured out the overall tau breaking rate and then multiplied it by the totals. If you just want to go to any one cell, okay, and you want to find the expected value of any one cell, this is how you do it. It's very simply the row total times the column total divided by the grand total. Row times column times grand total. Let me go back to this just so you can see one, right? So let's say I want to do the 18, that spot. So it's the row total, which is 45. All right, hang on, let me do this. Let's go back to the since we've already done that, so you can see how it works, actually. So let's do this one. So it would be the row total, which is 30, divided by It's going to be row times column divided by the total, right? So notice the row over the total is that 30 over 75, which is that 40% I got, right? And then times the column total, which is the 25. So you can see it's the same math. But if you're just looking for any specific cell, it's row total times column total divided by the grand total. I'm going to show you a little quicker way to do this in class. But for now, that's kind of the process you have to go through. And then some sort of conclusion and context. So let's do an example. We'll walk you through one. I'm actually doing an example page 599. I'll read it to you. I have the data right here. You don't have to actually look at it, but in case you want. It's basically, we have a Gallup poll results. It was a poll on family values in different nations. So I don't know what the question was. For you personally, do you think it's necessary or not necessary to have a child at some point in your life in order to feel fulfilled? Okay, so these were the results from that data we asked, and they actually asked the same amount of people in each country, so you can see it here. Okay, so let's just walk you through everything. This is called a, chi-square test of homogeneity. We're going to just say independent simple random samples. We're going to go check on that one. Okay. Each outcome, just because they told us that, each outcome falls into one cell. Like there's no people that can be in different cells, right? Falls into different cells. By the way, the answers were yes or no or undecided or I don't know. That's why I have that question mark. Each outcome falls in a different cell. And then each expected value greater than or equal to 5. So I would have to find all those, right? I'm going to write them in red. I actually have those numbers here. I'm not going to write them all down. This is 616. This is 354. This is 30. I'll do one more column. 616, 354, and 30. So we could do that for everyone. And then what we would do is we would actually write that matrix, right? So we would have this 1, 2, 3, 4, 5 by 3 matrix. 616, 354, 30. We would write those in there. Okay. I'm not going to save us a little bit of time right now doing that. And again, I'll show you a little quicker way in class. But for now, yeah, usually this is a pretty big matrix, and most of them aren't really that big. But for now, we'll leave it there. The null hypothesis would be the proportion of people. So you want to just write this out, who said yes, no, and undecided. So you want to list the categories. Undecided are the same for US, India, I'm going to abbreviate a little bit here, Mexico, Canada, and Germany. So you want to list out the proportions of each category is the same for each population. The alternate is they are not the same. You could just say that. I can be really quick on this one. We're going to be more specific when we answer the final question, right? Because remember, my final question is going to be about the alternate hypothesis. But for now, we'll do that. All right. We need a critical value. So I'll find that with you. The degrees of freedom. This is go back to my chart. 1, 2, 3, 4, 5 by 3 chart. So 5 by 3, I just write it like this, 4 by 2, 8 degrees of freedom. So real quickly, I'm going to go back to my chart. We'll go 5% since no one has said anything else to me in this problem. They could change that percent, don't forget. We're going to go 5%, 8 degrees of freedom, 15. So my cutoff's a little further over, right? 15.51. Okay. Go back to my test here. And we'll write in a little 15.51 here. My chi-square test statistic is observed minus sum of observed minus expected square root. I've already done all this work this time. I was smarter than last time. Again, you just list one. You can manipulate this, right, and put them in there as lists as you want. You can do it all manually if you want, but if you put all of the cells as list 1, all of the observed cells, all of the expected cells as list 2, and then your list 3, you just do observed minus expected squared over expected. It actually turns out to be a really, really big, gigantic test statistic, gigantic, right, way past the cutoff, which you could probably see if you just look at the data. You look at the data, you can kind of see they don't look very close, right? They're not close enough for us to wonder. You got 460 in US, you got 930 in India. And that's easy to see, by the way, because the totals are the same. But remember, if the totals aren't the same in each column for each country, if you've surveyed a different amount of people, then it can become a little more difficult to visually see it. That's why we do the test, right? P-value. P-value is chi-squared CDF from 628 to infinity with 8 degrees of freedom. It's basically 0. Yeah, I'm not even going to do that on my calculator. I'm sure it's going to tell me it's a big fat 0 on the calculator. We're going to reject the null. Evidence that proportions are different across the countries or something like that. You could use the same wording that I used at the beginning. You could just say there is no evidence that the proportion of people who said yes, no, undecided are the same for US, India, Mexico, Canada, and Germany. Sometimes I like to shortcut a little bit, so I'm not writing so much, but either way. And again, I'll show you a little quicker way to do the math in class. But for now, just you got to do cell by cell. And again, most of the problems have like 6 cells, 8 cells maybe. It's pretty unusual to get 15 cells. But then that's the beauty of those lists, right? You can use those lists to at least do the math for you. Alrighty, so that's it for section 10.2. I'll see you in class.